everyone, I'm Dr. Rizwana, working as a Professor of Physics in Institute of Aeronautical Engineering. Today we are going to discuss different types of questions that can be asked in Module 1, that is quantum mechanics. So first we are going to discuss short questions where we have of course answers being given in one or two lines. So coming to those questions, first one, relate quantum mechanics with classical mechanics. So in this case, we are going to talk about first classical mechanics. We'll say that classical mechanics, of course, it talks about non-relativistic motion of huge bodies or celestial bodies like planets, okay, and of course stars. So here we talk about motion of very like big bodies, and here when we talk about classical mechanics, we talk about continuous energy levels, and also here, we say that a particle, it can be moving with any energy from 0 to infinity. But when we take this classical mechanics, it fails to explain certain phenomena like photoelectric effect, Compton effect or Raman effect. So in order to go for this explanation of these phenomena, then came our quantum mechanics. And classical mechanics, it fails to explain motion of very small bodies or microscopic bodies. When we talk about atomic dimension, when we talk about motion of particles like electrons, protons and neutrons, classical mechanics fails. Here comes our quantum mechanics, where it talks about the motion of atomic dimensions or particles like electron, protons and neutrons. And this quantum mechanics conveniently is able to explain phenomena of Compton effect, of course photoelectric effect, and as well as Raman effect, and even Planck's black body radiation also it can be explained using quantum mechanics. And here completely quantum mechanics, it talks about discrete energy levels. So here it won't talk about continuous energy levels, it talks only in terms of quantization of energy. And what you will observe here is, here energies are explained by taking into consideration different quantum numbers. So this is what we have to write when we are comparing classical mechanics with quantum mechanics. So classical, it is for macroscopic bodies, huge bodies, where we talk about continuous energy levels. Whereas quantum mechanics, it is for smaller dimension or smaller particles, where we consider discrete energy levels. Then coming to second question, what is quantum mechanics and what does it explain? So here quantum mechanics, it talks about motion of atomic dimensions, very or microscopic quantities like electrons, protons and neutrons. Here it talks about discontinuous energy levels, where we have discrete energy levels. It talks in terms of energy packets known as the photons. And because of this quantum mechanics, we are able to explain very important phenomena like black body radiation, where we have spectral distribution of energy. And also we talk about phenomena like photoelectric effect, Compton effect as well as Raman effect. Then what is de Broglie's hypothesis of duality of material particles? So here de Broglie, he has taken into consideration wave-particle duality of light, where we say that light radiation, it exhibits properties of both wave and particle. So just like this light radiation, even different fundamental particles of physics like electron, protons and neutrons, where we are taking into consideration material particles, if these material particles move, they'll behave as a wave, and that wave is nothing but matter wave. The next, to show that de Broglie wavelength is expressed in terms of momentum and kinetic energy. So here what we are going to do for that, of course we are going to make use of Planck's theory, which talks about energy of photon as E is equal to h nu, and also we make use of Einstein's theory, which talks about mass energy relation E is equal to mc square. By taking these two equations, this equation, it will give rise to hc by lambda. If we compare these two equations, then we have our lambda as h by mc, and if we apply it to a material particle, this wavelength, it will become h by mv, and we know that mv is nothing but momentum. And if I want to write in terms of kinetic energy, it will become momentum. It is square root of 2 into mass into kinetic energy of the particle. Now, relate the concept of light radiation with wave-particle duality. So here, what you will observe here is, if you take a light, and if we consider phenomena like interference and diffraction, it will behave as a wave, because for these phenomena we require presence of two or more waves at the same position at the same time. We cannot expect two particles to be present at the same position at the same time. So that's why we'll say that if we take phenomena like diffraction and interference, our light radiation, it is behaving as a wave. But whereas if we take phenomena like photoelectric effect and Compton effect, where light radiation, when it interacts with the matter, it interacts as if it consists of particles known as photons. So if we take these phenomena, here light is behaving as a particle, and this shows that light, it has property of both wave as well as particle. Now, what are the two concepts taken into consideration to arrive at de Broglie's wavelength? So, one is our Planck's quantum theory, another one is Einstein's mass energy relation. So, we are taking these two concepts in order to derive expression for de Broglie's wavelength. Write different forms of de Broglie wavelengths of an electron. So, we have lambda is equal to h by mv, where m and v are mass and velocity of electron. And also we can write it as h by p, where p is momentum. And we can write in terms of kinetic energy as h by square root of 2me, where E is kinetic energy of the electron. And when we talk about electron, we know that how we can make electron, we can make it move by applying potential. In that case, wavelength, it is given as 12.26 by square root of V angstroms. What is V here? V is potential in volts. Then next, what is wave function? What are its applications? So what is wave function? First of all, wave function, it represents displacement of a wave associated with matter. And this wave function, generally they are complex wave functions. And also these wave functions, they'll like according to Schrodinger, they'll define amplitude of matter wave at a particular point in space. And coming to its applications, using this wave function, we are able to find probability, like what are the, like if we select one particular point in space, what are the chances of finding particle at that particular point in space can be found using this wave function. What is normalization condition from physical significance of wave function? So what is normalization condition? According to normalization condition, probability of finding particle at a given point in space, it is taken as unity. And what is the probability of finding particle in entire space? It is given as mod psi square dx dy dz. So because we are integrating it, and what are the limits of integration? Minus infinity to infinity, because we are talking about entire space. And mod psi square, what is mod psi square? It will give you probability density. And when we are multiplying it with dx dy dz, so probability of finding particle in a small volume dx dy dz. And if we integrate it, we are talking about probability of finding particle in entire space, and this probability it is taken to be 1. It means that there are full chances of finding particle in entire space. When we take such probability to be 1, that condition is said to be normalization condition. Then explain physical significance of wave function. So coming to physical significance, here we have to say that wave functions, usually they are complex, and they are not measurable, and they are not observable, so they don't have direct physical meaning. In order to get direct physical meaning, we have to multiply these complex wave functions with their complex conjugate. Then we are going to get mod psi square. Okay, and this mod psi square, it will give direct physical meaning, and it is observable also. And according to Schrodinger, what is mod psi square? It represents charge density, and according to Max Born, this mod psi square, it represents probability density. List any two properties which reveal the behavior of matter waves. So first property is, of course, by taking into consideration wavelength, lambda is equal to h by mv. Now, if you consider a particle whose mass is less, then wavelength associated with that matter wave will be larger. And whereas if particle into consideration is moving with less velocity, then greater will be the wavelength. Now, write expression for time-independent Schrodinger's wave equation. So, if you consider three-dimensional motion, so here in this case, Schrodinger wave equation, it is written as del square psi plus 2me minus v by h cross square psi is equal to 0. So, this is time-independent Schrodinger wave equation. What is the principle used by Davison and Germa to explain the wave nature of electron? So what Davison and Germa have done, they have taken electron, they have accelerated by applying potential, and once your electron is moving, then what they have done, they have applied Bragg's law of diffraction by considering that electrons are getting scattered from a particular scatterer, and he has used Bragg's law, that is nothing but 2d sin theta is equal to n lambda, and this is for diffraction. And whatever lambda value we got using this Bragg's law of diffraction, it is applied to de Broglie's hypothesis. And according to de Broglie's hypothesis, how we can find wavelength? 12.26 by square root of V, where V is in angstroms. And he has seen that wavelength calculated from Bragg's law and wavelength calculated using de Broglie's hypothesis, they came out to be same. So that's how he explained that electron, when it is made to move, it will behave as a wave. Explain experimental setup of Davison and Germa's experiment. So if you consider experimental setup of Davison and Germa's experiment, here in this case we are going to have one electron gun. So if you take here Davison and Germa's experiment, we are going to have electron gun. And this electron gun, it is applied to electric field in order to apply potential. And then after that, what we are going to do here, as you can see inside this electron gun, this is a tungsten filament. This tungsten filament is heated to dull red so that electrons are emitted by thermoionic emission. And then these electrons which are coming from this element, they are accelerated by applying a potential. Then we have electrons which are moving with very high velocity. They are made to fall on nickel target. Okay, and once electrons falls on this nickel target, they get scattered in different direction. Those scattered electrons, they are made to enter electron collector. So this is the electron collector or Faraday's cylinder. So we have electron collector, and this electron collector, it is made to move on a circular graduated scale in order to know direction. So this whole apparatus, it is kept in vacuum so that electrons will not lose energy when they interact with particles of air. So this is the experimental arrangement of Davison and Germa's experiment. Summarize the observations in Davison and Germa experiment. So here what we have done, we have taken electrons and we made them move, okay, and then after that we have connected scattered electrons, and what we have observed here is number of electrons scattered. The number, it will be different in different directions, and what we have observed here is for a particular potential V, the scattering curve, it is going to show peak in one particular direction, and this will give us direction in which maximum number of electrons are getting diffracted. And once we get that particular direction, using that direction we are going to find a wavelength of diffracted wave, and this wavelength, it is matched with wavelength calculated using de Broglie's hypothesis. Then for the conclusion, so coming to conclusion of Davison and Germa's experiment, because electron, when it is made to move, and by considering its diffraction by using Bragg's law, whatever wavelength is calculated, it comes out to be same as wavelength calculated using de Broglie's hypothesis, because both wavelengths are matching. So that's why it has concluded that de Broglie's hypothesis of existence of matter wave is correct. Then what are the expressions for wave function and energy of particle? So when we are considering here expression for the wave function, so if you take sin x, so it is given as, if you take one dimensional motion, it is square root of 2 by L sine of n pi by L x. So it is about the one dimensional motion. Whereas when you take into consideration here three-dimensional motion, so you are going to have 2 by L, square root of 2 by L whole cube, and then sine of, so here we are going to have nx pi by Lx, and then sine of ny pi by Ly, and then sine of nz pi by Lz. Okay, so where nx, ny, nz, these are the quantum numbers associated with three directions x, y, z. And when we talk about energy En, it is given as nx square plus ny square plus nz square h square by 8 L square. So this is the energy for potential box, three-dimensional potential box. Explain the assumption for electron to consider it in a potential wave. So here, what is the assumption? What we have done, we have considered one-dimensional motion of electron, and then at two regions along the x direction, we have applied infinite potential, and those regions we are taking it as x is equal to 0 and x is equal to L. Then what happens to our free electron? It will become bound electron because it is not able to penetrate through this infinite potential. And coming to eigenfunction for one-dimensional motion, sine x, it is given as, of course, as I have already given, square root of 2 by L sine n pi by L x. And coming to energy, it is given only in terms of one quantum number n, so it will be n square h square by 8m n square. So these are the short questions in quantum mechanics. Then coming to long questions, what are the key points in introduction of quantum mechanics? Already have discussed. Here we talk about discrete energy levels, and it is applicable to smaller dimensions. And of course, here we'll take into consideration different quantum numbers. So we have to write all those points. And when we are talking about comparison of classical and quantum, we have to say that classical, it talks only about motion of huge bodies and talks about continuous energy levels. But when it comes to small dimensions, it fails, and that was later it was taken by discrete energy levels or quantization of energy, which is taken by quantum mechanics. Then compare a particle with a wave and discuss about dual nature of radiation. So already have discussed, when you take a light radiation in phenomena like interference and diffraction, it will behave as a wave where we have presence of waves at the same time at the same point. That is not possible with a particle. Whereas if we take phenomena like photoelectric effect and Compton effect, your light radiation, when it interacts with the matter, it behaves as if it is interacting through its particles known as the photons. And explain Max-Born interpretation. According to Max-Born interpretation, probability of finding particle in entire space, it should be equal to 1. This particular condition, it is called as normalization condition. Now, how to derive an expression for wavelength associated with electron accelerated by potential? So in this case, when we take an electron which is accelerated by potential, then its kinetic energy EV. So it is given as half mv square. So if its kinetic energy is E, and we know expression for de Broglie wavelength in terms of kinetic energy, it is given as 2me. So here we end up having it as 2mev. Now we know value of H, Planck's constant, 6.6 into 10 power of minus 34 joule second, mass of electron 9.1 into 10 power of minus 31 kilograms, charge is 1.6 into 10 power of minus 19. So when we do it, our expression, it comes out to be 12.26 by square root of V angstroms. Then show that expression for wavelength associated with electron. So it is lambda is equal to h by mv. Here we make use of two concepts. One is Planck's law. What is Planck's law? According to Planck's law, E is equal to mc square, which is E is equal to when we talk about Planck's law, E is equal to h nu, which is hc by lambda. And if we consider Einstein's theory, E is equal to mc square, and if we compare both these equations, we'll have wavelength of photon as h by mc, and if we apply it to material particle which has got mass m and velocity v, it will become h by mv. And next one is explain de Broglie's concept of matter wave. So according to de Broglie's, just like wave particle duality of light radiation, even material particle will also have dual characteristic. If a material particle moves, it will behave as a wave, and that wave associated with moving material particle is nothing but matter wave. And here we have to discuss different properties of matter wave, which show that matter waves are not electromagnetic waves but new kind of waves. And if you consider like expression, what is that expression? Lambda is equal to h by mv. In this expression, we can observe that this particular expression, it is independent of charge. So it means that our matter waves, they are generated whether particle in motion is charged or uncharged, whereas electromagnetic waves are generated only with moving charged particles. And the next is here, velocity of matter wave, it depends upon velocity of material particle, which is not constant, but velocity of electromagnetic wave is constant. And then we know that electromagnetic waves, they cannot travel with velocity greater than velocity of light, but our matter waves, they travel with velocity greater than velocity of light. So if we consider all these properties, we can say that matter waves are not electromagnetic waves but new kind of waves. Now this show that wavelength. So using Planck's, already we have discussed it, and with respect to energy as well as with respect to mass and velocity. Then summarize the construction, already have discussed, where we have electron gun. Okay, and in electron gun we have tungsten filament which is heated to dull red, and then it is accelerated by applying potential. Then these fast moving electrons, they are made to fall on nickel target, and scattered electrons, they are collected in different directions by using electron collector or Faraday cylinder, and this electron collector, it is moved on a circular graduated scale. So this is the construction. And how did Davison and Germa explain the proof for that, what they have done? So they have once they have performed experiment, they are able to get with respect to angle theta intensity of electrons scattered, and from scattering curve they have observed that for an electron which is accelerated by potential 54 volts, it has got maximum angle of diffraction at 50 degrees. When we consider nickel crystal with different planes, we have observed that this angle between the incident beam and diffracted beam is 50 degrees. But I need to find this theta value. So this is 90 degrees. So 90 minus, we know that 54 volts. So here what we have observed here is, so this angle, which is a difference of, when we take 54 volts angle, and this angle is of course 50 degrees, and when we divide it, it will become 25 degrees, and this one is total 90 degrees. So our theta, it is 90 minus 25, so it comes out to be 65 degrees. So now he made use of Bragg's law, which is 2d sin theta is equal to L lambda, and we know that interplanar spacing for nickel target, it is 0.091 nanometer into, we got a theta, which is angle made by either incident beam and diffracted beam with the Bragg's plane, which is 65 degrees, and maximum diffracted order is 1. So from this he has calculated lambda, which has come to be 0.166 nanometer, and then he made use of de Broglie's formula for electron, which is 12.26 by square root of V angstroms, and in this case V is 54 volts, and he got his wavelength as 0.165 nanometer, and experimental value and theoretical value, both of them are same. So that's why he has concluded that when you make a particle move, it will behave as a wave. Now extend the concept of dual nature and arrive at Schrodinger's time independent wave equation. So in this case, what we are going to do here, we are going to take classical differential equation of wave motion. What is the classical differential equation? So it is dou square psi by dou t square is equal to v square del square psi, where del square is the Laplacian operator, and he has taken solution for this differential equation as psi naught e to the power of, so here in this case he has taken e to the power of ikx, and he has found this dou square psi by dou t square value, and then he has substituted in this equation. Then after that he made use of Bragg's law, which is de Broglie's hypothesis, where lambda is equal to h by mv, and then he has expressed total energy E and potential energy V in terms of kinetic energy, that is half mv square. So in this case, m square v square, it comes out to be 2m e minus v. So when he has applied this in this classical differential equation, so here we got Schrodinger equation as 2m e minus v by h cross square psi is equal to 0. Then show that permitted energy levels of a particle. So for that we have to construct a potential box by taking x is equal to 0 and x is equal to L. Then after that, we have to make use of Schrodinger's wave equation, which is dou square psi by dou x square plus, this is for one dimensional motion, and inside the box potential energy is 0. So 2me by h cross square psi is equal to 0. After that, he has taken this particular value to be k square, and he has written solution for this equation psi as a sin kx plus b cos kx. Then by constructing boundary conditions, we'll try to get constants A and B. And also during this, what are the boundary conditions? Wave function, it will become 0 at x is equal to 0, and also it will become 0 at x is equal to L. These are the boundaries, and when we apply these boundary conditions, we'll get our constant A to be 0, whereas, constant B to be 0. Then psi of x a sine, and when we substitute second boundary condition, here what we'll observe here is k, it comes out to be n pi by L. So it is n pi by L x. Then after that, we made use of normalization condition, which is 0 to L mod psi x square dx, it has to be equal to 1. After simplification, we got our constant A as square root of 2 by L. So finally, our wave function, it will become square root of 2 by L sine n pi by L x. And then in order to get energy, of course, here we are defining k square as this, and of course we are defining k as this. So if we compare both of them, where we take k square to be 2me by h cross square, and also n square pi square by L square. If we simplify, we got our energy as n square h square by 8m L square. Okay, and interpret the results. So what are the results or conclusions of applications of Schrodinger wave equation? So for that, we need to take a graph. So in this graph, when I try to plot both the wave function here, of course between the boundaries, x, this is for x is equal to 0, and this is for x is equal to L. If I consider wave displacement for different values of n is equal to 1 and n is equal to 2. So we got such type of displacement. And similarly, if I take, so this is psi 1 and this one is psi 2. And if I take probability density for those two quantum numbers, n is equal to 1 and n is equal to 2, these are the shape of graphs. Okay, so we have to explain here how, like if we take electron whose energy is corresponding to n is equal to 1, then maximum displacement is at the middle of the box. Whereas if we take same electron whose energy is corresponding to n is equal to 2, then its maximum displacement is at 1/4 distance. So this is L by 4 distance from either sides of the box. Okay. And when we consider this probability density, probability of finding the particle is maximum at the center of the box, whereas here probability is 1/4 distance from either sides of the box. So, and summarize the conclusions of applications of Schrodinger's wave equation. So just now we have seen that potential wave, we talk about energy levels. So in this energy levels, we talk about discrete energy levels. So what about the discrete energy levels? For different values of quantum numbers, we are going to have, suppose if we take this potential well, here these energy levels, they are well separated from each other. So for different values of quantum numbers, we are going to have different values of energies. This is known as quantization of energy. And another point is, here energy, it is inversely proportional to square of width of the box. Then coming to numericals, first numerical, calculate velocity and kinetic energy. Here wavelength is given, lambda value is given, which is 0.21 nanometer. So in order to find, we know that de Broglie wavelength is h by mv. From this, velocity can be taken as lambda, h, v is equal to h by m lambda. And once we know velocity, how we can find kinetic energy? By using half mv square. And then coming to second problem, here we are given velocity of light. Velocity of light is 1/10. Velocity of material particle is 1/10 the velocity of light, and we know what is the value of velocity of light, 3 into 10 to the power of 8 meters per second. We are given mass, so how to find de Broglie wavelength? By using formula lambda is equal to h by MV. Then coming to third problem, here we make use of this formula 12.26 by square root of V angstroms. And what is V? V is equal to 15,000 volts because it is given in kilovolts. And here we have to find de Broglie wavelength. Here kinetic energy is given, E value is given, which is 0.025 electron volts. We have to convert it into joules by multiplying it with 1.6 into 10 power of minus 19. And then finally we'll make use of this formula, lambda is equal to h by square root of 2me. And here in this case again, V is equal to h by m lambda and kinetic energy is half mv square. And here we make use of this formula, lambda is equal to 12.26 by square root of V angstroms. And coming to this energy associated, so in the last four problems, we are going to make use of this formula. En is equal to n square h square by 8ml square. In this problem, what is the value of L? L is given as 10 to the power of minus 9 meters. And here, find the lowest energy. When we talk about lowest energy, we are talking about n is equal to 1. And here, we are talking about ground state energy, n is equal to 1. And first two excited state, we have to substitute n is equal to 2 and n is equal to 3. Or simply, once we find even value by making use of this formula, h square by 8m e square, then how to find first excited state? It is 4 of even. And what is the energy of second excited state? It is 9 of even. And coming to last problem, when we talk about minimum energy, we have to substitute n is equal to 1 in this particular formula. So today I have discussed different questions, short as well as long, as well as problems, numericals in quantum mechanics. So with this, I'm going to finish my video here. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.